All right, we're back with Atwood machines, and they're slightly different than they were in Physics 1 because these now we're gonna talk about pulleys that actually have mass and friction involved. And last year in Physics 1, you didn't ever have to consider that. Okay, um, okay, so example number one is where the pulley actually does have inertia, and so we actually do have to consider that when we are getting the net force on the pulley. Okay, so we want to figure out the force action on the two masses on the pulley and determine the acceleration of the system of masses. Okay, so I'm going to use green for my little mass here on the left. Okay, if I were to draw my forces, I would actually have, so the bigger mass is going to fall, this is going to rise, so it should have a greater amount of tension force, okay, going up, and then it should have a smaller amount of mg going down, okay? So my net acceleration should be going up here, okay? For the big M, okay, which I'll do here in pink, okay, I should have a greater mg, capital M, g, okay, and then going up should be a smaller amount of tension, okay? And my net acceleration for this one should also go straight down, or should, not also, but should go straight down. Okay. Okay. I need a. Let me get my light blue for this. So just because I like to match the color in my key, so I'm kind of picky about it. Okay. There's my light blue. So now I actually have to consider what's on the pulley. Okay. The pulley, when this system is released from rest, the big M is going to fall, this M is going to rise, which is actually going to mean that the pulley is going to have to rotate clockwise, right? So my angular acceleration is going to go this way, okay? And I have a torque being applied from the right tension, okay? And then I have a torque being applied from the left tension, okay? I labeled them a little bit differently in my notes here. So it should be, I'm going to call this TL, okay, TL, and I'm going to call this TR, okay, for tension left, tension right, okay. So when I write my Newton's second law equations, okay, for little m, what I'm doing is I'm doing TL minus mg equals ma, little ma, okay. For my big M, I'm doing big M, okay, equals big M G minus the tension force in the right equals big M A. Okay, nothing too crazy yet. But then I have to consider the pulley, okay? Pulley, all right? I'm going to break off a little section over here to work out how the pulley works, okay? Here's how we solve for the pulley, and it works pretty much the same in both cases, okay? I don't need to, in the second one, I'm going to skip solving it because I've already shown you how to do it, okay? To do the pulley, you just have to recognize that the net torque is equal to I alpha, okay? And the net torque is also just R times the net force, right? So I'm going to do the radius because the radius is R, and the net force is going to be you're going to have to subtract the two tensions. So it's going to be TR minus TL, okay? And I'm going to set that equal to I, which is kmr squared. It actually tells me what the moment of inertia is right here. Km sub p r squared, okay, times the acceleration. Now, I'm actually going to use the fact that alpha is equal to a over r. So I'm going to plug that in there, and I'm going to get a over r, okay? And what I should recognize is that this R is, I'm actually going to be able to cancel out all my R's completely, okay? This R actually cancels out entirely because you take out an R from the one on the left side and you take out the R right there. So all of my R's are canceled out completely. And I end up with TR minus TL equals Km sub P times A. Okay, that's actually it. That's the pulley equation right there. So I would do TR minus TL equals K mass of the pulley times A. And then when I combine everything to get my equation for the whole system of masses, okay, I'm just going to take the subtraction of the two masses, mg's, okay, capital Mg minus lowercase mg, okay, equals, okay, little m plus big M, okay, plus k mass of the pulley times acceleration, okay? My net mass times acceleration. The reason I'm using kmp is because that's the rotational mass in a way of the pulley, okay? So that's what's important, okay? So net force, okay, ma, okay? In this case now, we have a mass resting on a table and there is friction on the table. So if I draw my forces, okay, I'm going to get a normal force going up here. I'm going to get, there's a friction force that's opposing the motion. Okay. I'm going to get little mg right here. And then I'm going to get, there's a tension here. I'm going to call this T sub T for tension of the top mass. This one I'm going to, this one over here is only going to have mg, big mg. Okay. And then it's going to have tension. I'm going to call this tension, oh, sorry, tension hanging, okay, for the hanging mass tension. Well, then if I'm looking at the pulley, I'm going to have the tension on the top here by Newton's second law, or sorry, Newton's third law, okay, and then tension of the hanging mass, and the acceleration should then kind of curve that way, okay? So I'm going to write the exact same equation for this, except now what I need to do is I actually have to consider the friction, okay? So when I do the green, so little m, okay? Or sorry, actually, let me start with big M, because big M is the one that's accelerating down. So let me start with that one, okay? Big M. Don't really think it makes a difference, but I'm kind of paranoid about it needs to be like the same as my notes key, okay? Big M G minus the tension for the hanging mass, okay, is equal to big M A. Okay. Oh gosh, dropped my green pen. Okay. Little m, okay, is going to have tension force to the right, minus the friction force, okay? Friction force, by the way, is mu mg in this case because it's on a horizontal surface, okay? Minus mu mg equals little ma. Okay, pulleys, the pulley, believe it or not, it's going to be the exact same as it was before. Tension hanging minus tension from the top equals k m sub p a. Exact same as before. The only difference is that now we have this friction term right here, okay? And then all I got to do, okay, is just, when I combine the equation, I end up getting big M G, because that's the prevailing force, minus mu mg, okay, equals the sum of all the masses, big M plus little m plus m sub p, okay, a. And then you can get a by itself to get the expression for the acceleration, okay? It's not that hard. You just divide what's in the parentheses here on both sides, and the equations look very, very similar. The only difference is that you do have to consider friction in example number 2, okay? All right, well, those are Atwood machines for Physics C, okay? Enjoy.